In this video, we're going to talk about the behavior of our capacitor in a DC circuit, meaning when we apply a DC voltage to the circuit. So before we dive right in and talk about the behavior of this capacitor, I want to talk about a mathematical function. We call it the exponential function. Mathematically, we write this as e to the x, and it describes a situation where we have some value that starts at 0 and rises very quickly, and I'm going to leave that out, and I'm going to make a couple of translations to that. So if we instead looked at e to the minus x, that would change the behavior in this way. Instead of starting at 0 and then rising very quickly toward the end, it's actually going to start at 1 and drop really quickly in the beginning. Okay, and one more function I'd like for you to be familiar with: if we took that e to the minus x and we subtracted it from 1, we would get the opposite behavior that we saw in the previous graph. And that's that it would start at 0 and go up to 1 very quickly. Okay, so these are the two relationships I want you to become familiar with. The e to the minus x, we say that describes the behavior when something starts at a maximum value and then goes very quickly to 0. And then we say that 1 minus e to the minus x is a value that would start at 0 and then goes very quickly to a maximum value. And what that maximum value is, if we leave e to the minus x and 1 minus e to the x alone, the max would be 1 in those cases. However, if we multiplied it by, for instance, let's say a maximum voltage, well, that means that for e to the minus x, we would start at that maximum voltage and then go to 0 over time. This x-axis is describing a time relationship. So here starting at 0 seconds and here at infinity, or as many seconds as you're describing there. And 1 minus e to the minus x, if we multiplied that entire relationship by V max, then we're looking at something that starts at 0 and climbs to a maximum voltage, again, over time. It's going to take some time. All right, so now that we've looked at the mathematical relationship we need in order to describe this, let's talk about the capacitor operation. So when we apply current to our capacitor, this is going to take some time to respond. It's not going to be like your resistor, where when you apply a current, you have a voltage drop immediately and there's no time dependency. The capacitor is actually going to take some time. It's actually storing charge, and it takes time to do that. So we're going to look at a couple of different phases of operation. In this video, we're going to talk about the charging phase, and that's where we have no voltage or no charge stored across the plates of the capacitor, but we're going to gradually do that over time. And we'll talk about steady state just a little bit. We might follow that up with another video later, but we'll talk about what happens after that capacitor is fully charged, or after we open the switch. The discharging phase is when we allow the capacitor to release the energy back into the circuit, and we'll talk about that in another video as well. Okay, so let's go back to the charging phase. So when we apply a DC voltage source to our capacitor, the capacitor is going to start to store charge, and this is going to take some time to do, and we'll explain how to figure out how long that happens and what happens there. But essentially what happens is when we close this switch and our current starts to flow through the circuit, we start to build up our negative charges on one of the plates and our positive charges on the other plate. Once we get to a point where we have stored basically all of the voltage that we have in the circuit in this case. Then what we see is that our voltage drop across the plates, if we had a voltmeter there, we would see that it equals the source voltage in this circuit. Once that happens, we get to a point where we reach steady state and the capacitor is not going to charge any more than that. And at that point, there's no current flowing through the circuit anymore. Okay, so let's look at what I mean by that. Okay, so when we close the switch, this is the beginning of the charging phase. And we will call that t equals 0 seconds. That means we just close the switch. Okay, it's going to change very quickly after that, but right at the point where we close the switch, here's kind of what the circuit looks like. We've got my voltage source there and my resistor, but the capacitor doesn't have any voltage stored across it at this point. So the V sub C, that's the voltage drop across the capacitor, at this point is 0. Okay, so right at t equals 0, our voltage across our capacitor is 0. Our current through that capacitor is the same thing as our source current. And you know that the source current in this case would just be E over R. Okay, just Ohm's law. And then our voltage drop across our resistor would be IC times R. And in this case, that would just equal E. Okay, so this is the very beginning of the charging phase, and it doesn't last. As soon as we start charging that capacitor, all of this changes. But this is what's true right at the beginning of that charging phase. Now at the end of the charging phase, let's look at what's happening. Okay, at the end of the charging phase, remember, that's where our voltage drop across the capacitor is going to equal the supply voltage. Okay, so what does that look like? That looks like our E, our R, and over here our cap now, since V equals E, that basically means that our capacitor looks like an open circuit at this point. Okay, think about Kirchhoff's voltage law. Kirchhoff's voltage law says that the sum of the voltage rises minus the voltage drops around a closed loop has to equal 0. If my voltage rise is E and my voltage drop across the capacitor is E, then I have no voltage drop across R. If I have no voltage drop across R, I have no current. So at the end of the charging phase, we would have no current through that capacitor, and the voltage drop across R would simply be 0. Okay? So in the beginning of the charging phase, your capacitor actually looks like a short circuit. There is no voltage drop across it, but there is current. And in the end of the charging phase, your capacitor looks like an open circuit. Okay, there is a voltage drop across there, but no current in this case. Okay, so the charging phase is what's happening between there. So these equations that we're working on, that's going to describe what's going on in between. Okay, so in between the beginning and the end, we have this charging phase. So let's talk about how we would find the voltage across the capacitor, the current through the capacitor, and the voltage across the resistor during that charging phase. Okay, so remember what I said before, and that's that these equations describe something that starts at a maximum and goes to 0, or something that starts at 0 and goes to a maximum. okay? Let's look at our V sub C, the voltage drop across the capacitor. At the beginning, we're starting at 0. At the end, we have charged that capacitor up to E volts. That is something that starts at 0 and goes to a maximum value, okay, right here. So that's going to be the equation we're going to apply. 1 minus e to the minus x. We'll talk about what that x is in a minute. But then what is that maximum voltage we are, what is that maximum voltage in the end? In this case, it's E, okay? So what this says is that our V sub C is starting at 0 and going to whatever that maximum is, which happens to be E in this case. Okay, so that's E over time. Okay, and then let's look at what our current is doing. Our current, notice, is starting at E over R, and then at the end of the phase, it's actually 0. That's the other equation we talked about right here. Now, we're not going to use Vmax. We're actually going to use whatever the maximum current is. So that gives us e to the minus x, and that maximum is E over R. So what we're saying is we're going from E over R to 0 in a very quick, short time. And then what is our voltage drop across the resistor doing? Let me change that to resistor. VR is going from E to 0. What does that look like? Is that starting at max going to 0, or starting at 0 going to max? E to 0. So that is going, starting at E to 0, that is e to the minus x. So our equation there is e to the minus x, and the maximum value will be E. Okay, so notice the current and the voltage drop across the resistor have exactly the same shape, the same equation, because remember, they're related by Ohm's law. Okay, so as this voltage drop across the resistor changes, so does the current. They're directly proportional. So you'll see that they have the same graph. Okay, I'm going to stop the video here. Just want to show you these pictures, and then in the next video we will work a problem or two to go over this a little bit more. And we'll talk about the time constant in the next video as well. So for the capacitor voltage, or the voltage drop across the capacitor, our equation is that it's going to start at 0 and go to a maximum value in this particular circuit. That maximum value is E. We'll talk about that later. It might not always be E. But in this case, we're going to charge that capacitor up to the source voltage. And the shape of that curve, 1 minus e to the minus t over tau. So x is going to incorporate a time constant, again, that we'll talk about in the next video. The capacitor current is doing the opposite. It is starting at its maximum current and going to 0, as at the end of the charging phase, the capacitor voltage is at its maximum, and it's not going, and the capacitor is not allowing any more current to flow through the circuit. So that starts at max goes to 0, and notice that it's going to make, we'll talk about the time constant in the next video, but we'll see the percentage of that maximum value that we drop down very quickly. The resistor value has the same shape of the curve that you saw in the current will be starting at its maximum value, which was E, going to 0 in a very quick amount of time. And these would be the charging equations. We'll pick up in the next video where we left off here.